Hi everyone, let's work through an example that's just a little bit messier where we will use implicit differentiation to find a derivative, and then I'd like to use that derivative to find the equation for the tangent line when y equals -1. So our formula is x squared minus 5xy squared equals 7y to the fifth plus 1. And if we're looking for dy dx, then we'd like to take the derivative with respect to x of both sides. On the left-hand side, we have a difference, and on the right-hand side, we have a plus. So that's going to be the big shortcut that's determining the structure of our derivative. So if we start with, before the minus sign, an x squared, the derivative of x squared with respect to x is 2x. Again, if you're getting mixed up with when to use the d over dx's, you could use them every time. And what will happen is just that whenever it's a dx over dx, those are equal to 1. So you can just not write those out. After the minus sign, we have a 5xy squared. So let's think about that as 5x times y squared, and we'll use a product rule. So I want the y squared, the second, multiplied by the derivative of 5x, which is just 5, or if you're thinking chain rule every time, it would be 5 dx dx. Then we need a minus, and we have to be a little careful here. Either throw in some parentheses to make sure that minus applies to everything, or what I really did there was I mentally kind of attached the minus sign to the 5 to make sure that it makes it all the way through. This needs to be multiplied by the derivative of y squared, which will be a 2y, and don't forget to chain out a dy dx. Remember, we're thinking about that as function squared, and the derivative of some function squared is 2 times that function to the first, chain out the derivative of the function. That's what the dy dx is the chain. On the other side, I have a 7y to the fifth, so I'm going to use a power rule, 35y to the fourth, and then again I'm thinking y is a function, so the chain rule says you have to chain out the derivative of y with respect to x. I then have a plus, but the derivative that comes after that will be a 0, so I'm just going to leave that off. Okay, I think this is the first one where I'm going to have to do a little bit of rearranging just to get my dy dx's on the same side. So to start, I will add that, I'm going to, hold on, rewrite this for myself a little bit. This is like a negative 10xy dy dx. So I'm going to add that onto the other side, which means I'll have a 35y squared, y to the fourth dy dx, plus a 10xy dy dx. So I've gotten my dy dx's isolated on one side, but there are two of them, so I will have to factor. So if I factor out dy dx, I'm left with 35y to the fourth plus 10xy. And again, remember, just imagine distributing to check yourself. If it doesn't turn back into what you have written above, then you've done something wrong. All right, last step on finding derivatives. I have a single dy dx, but it's multiplied by a whole mess. So if I want to solve for dy dx, I need to divide by that whole mess. All right, so this is my derivative, and that's a perfectly good answer. One thing worth checking when you end up with fractions is, could I factor and cancel? And I do notice in the bottom, I could even factor out a 5y, and I'd be left with 7y cubed plus 2x. But I can't factor any y's or 5's out of the top, so I can't cancel anyway. So it's worth looking at that, but if you can't cancel, you don't have to write it in factored form. It really is just fine. Okay, so that's what you'll have to do for most problems, is just find the derivative, but I do want to connect this back to our tangent line problem that we did earlier. If we want to find the equation of the tangent line when y equals 1, What's a little bit new now is that to find the equation for a tangent line, we do need to know a y value. We also need to know an x value. We need both coordinates of the point when we get a formula involving x and y. So my first little bit of work will actually be to try and find the right x values. So I'm going to go back to my original formula. I'm looking for points on the function or the relation that I started with, not the derivative. So I'll have x squared. If I plug -1 in for y here, it becomes +1 because it's squared. So it's really just -5x minus 5x. On the other side, -1 to the 5th is -1, so I'll get a -7 plus 1, or a -6. That's looking quadratic, so I'm going to set it equal to 0, x squared minus 5x, and if this is a -6, then when I move it to the other side, it becomes a +6. And that even looks factorable. I think I want a -2 minus 3. So x equals 2 or 3. So it looks like there's actually 2 points with y equal to -1. And since it hasn't been specified for me, I could work on finding the tangent line at both of those points. So I will need dy dx evaluated when x equals 2 and y equals -1. And I will need dy dx evaluated when x equals 3 and y equals -1. Okay, so, sorry, jumping my screen around. Now I'm going back to my derivative formula, and I'm saying if x equals 2, then on the top I get 2 times 2, which is 4, minus 5 times -1 squared, which is just 1, so minus 5. On the bottom, I have 35 times -1 to the 4th, which is just 1. So I get 35 plus 10 times, what were we plugging in? 2 times -1, so minus 20. And that ends up being -1 over 15 for the slope for the first tangent line. For the second tangent line, we're interested in the point 3, -1. So in the top of that fraction, we'll get 6 minus 5, and in the bottom, we'll get 35 plus 10 times 3 times -1, which is -30, giving us a slope of +1/5. All right, now that we've got slopes, let's go ahead and build these equations. So the first line needs to go through 2, -1, which means we'll have y plus 1 equals -1/15 times x minus 2. So y will have to equal -1/15 x plus 2/15 minus 1. Remember, 1 is 15/15. So we end up with y equals -1/15 x minus 13/15. Okay, for the second equation, we want to go through the point 3, -1. So we'll again have y plus 1, but this time it equals +1/5 times x minus 3. So y is going to equal 1/5 x minus 3/5 minus 1. And again, 1 is 5/5. So putting that all together, we get y equals 1/5 x minus 8/5. Okay, so the last thing I'd like to do is head to Desmos and see what this thing actually looks like and check out these two tangent lines we're getting and make sure that they look like they actually fit. So this is a graph of our curve with our 2 points labeled, 2, -1, 3, -1. And notice there is that kind of funny line sitting along the x-axis, and it disappears as I zoom. I think what's happening there is just that Desmos connects the dots. So sometimes when your curve is unique enough, it can mess with it a little bit, but I really do think that's continuous. I don't think there's a jog in the middle. I do notice looking at this curve that it's definitely not a function. If I draw a vertical line here, or here, it definitely hits the graph 3 different times. So we're not passing a vertical line test. But it's a perfectly interesting relation, and we should be able to talk about tangent lines at 2 and at 3, and I can kind of visualize that. So let's turn those on. That's the tangent line at x equals 2, and that looks pretty good. Looks about like what I was visualizing. If I turn on the tangent line at x equals 3, I see that positive slope, and that one also seems to be doing a good job of following the curve. So we can absolutely find tangent lines to relations, and implicit differentiation is going to be the tool that allows us to do that.